In the diagram below of circle O, segment GO is 8 units long. The measure of angle GOJ, right there, that central angle, is 60 degrees. What is the area, in terms of pi, of the shaded region? Well, remember, I could just set up a proportion here. I could take the central angle, divide that by a full rotation of a circle, 360 degrees, set that equal to the area of the part, the area of just the sector, divided by the full area of the circle. One small problem is that they actually didn't give us the central angle. They gave us the central angle of the unshaded part. I care about the central angle of the shaded part. But that's pretty easy to figure out. If I know that all of a circle should be 360 degrees, I can subtract away 60 to find that that central angle I'm looking at is 300 degrees. So that's what I'm going to use in my proportion. 300 divided by 360 is equal to the area of the sector, which is what I'm looking for, divided by the full area of the circle. Remember that the formula for the full area of a circle is pi times my radius squared. In this case, my radius is just 8. So you could write that as pi times 8 squared, or if you know that 8 squared is 64, you could write that as 64 pi. Now to solve any proportion, the easiest and fastest way is to cross multiply. So 360 times x is 360 times x. But when I multiply 300 to 64 pi, I'm not going to hit the pi button in my calculator. I'm just going to multiply 300 times 64 to get 19,200. And there's still going to be a pi being multiplied to that. So I'm not going to touch that button in my calculator yet because I notice all of my answers have a pi in them. So to continue solving this equation, I want to isolate x, so I can divide 360 on both sides of the equal sign. And I can divide that 19,200 by 360 to find that I get 53.333333. I notice all my answers are fractions. So I'm just going to hit math, enter, and then enter one more time to find that that's 160 over 3, all being multiplied to pi. And that represents the area of that shaded sector there. So it's most of the area of the circle, but just 300 degrees of it, not a full 360 degrees. So answer choice 4. Number 2. A circle with a radius of 5 was divided into 24 congruent sectors. The sectors were then rearranged as shown in the diagram below to the nearest integer. What is this distance? Well, let's trace what each of these parts are. It's cutting it into little tiny sectors. And notice that this distance along the edge here, which then becomes that flat distance, is part of the circumference of the circle, the distance around the edge. Moreover, it's half of the circumference, because this distance up here is half the circumference, and this distance down here is also half of the circumference. So if I could just figure out what the circumference is, I could take half of that, and that would be the value of x. Remember, the formula for circumference is circumference equals pi times my diameter, and I'm told that the radius was 5, so my diameter is just 10 units. So that's my full circumference. To find half of that, I can just divide this by 2 to find that half of the circumference is 5 pi. But they asked for it to the nearest integer, so I'm going to have to round this a little bit. If I go into my calculator and just type in 5 and multiply it by pi, pi is right above the caret key there, I get that this is about 15.708, or if I round to the nearest integer, 16. Number 3. Given triangle ABC with A is 2, 3, B is -4, 5, and C is -1, -2, find the perimeter of ABC to the nearest tenth. Well, the perimeter is going to be the distance around the outside, so the sum of all 3 of those sides. And to find the length of any of them, it would be helpful to use the distance formula. Remember that the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. And I'll just find the length of one of them because the process is the same for all of them. If I want to find the distance for, let's say, AB, that side, I can treat A as my x1, y1, and B as my x2, y2 when I substitute into the formula. So negative 4 minus 2 squared plus my y2 minus y1 squared. Now when I type this into my calculator, I'm going to type in everything except for the square root sign. So I'm going to use parentheses just like I have it. Negative 4 minus 2 squared plus, and then I'll use parentheses again, 5 minus 3 squared. I check to make sure that it looks exactly like what I have written down there, and I find that that's 40. So the side length AB is radical 40. It says to the nearest tenth, but I want to wait till the end to calculate that to the nearest tenth. Now, if you use the distance formula for the other sides, which, the process is exactly the same, just with different points, you'll find that the distance between B and C is radical 58, and the distance between A and C is radical 34. So if I want to find the perimeter, I would add up all those sides, radical 40 plus radical 58 plus radical 34. And again, I don't want to round this till the very end, so when I type this into my calculator, I'm going to type it in exactly like that. Radical 40 plus radical 58 plus radical 34. And if I round that to the nearest tenth, that's about 19.8 units. So I use the distance formula when I'm finding the perimeter. Part B says find the area of triangle ABC. The fastest way to do that would be to box this guy in. So I'm going to draw a nice rectangle around this figure here. I'll do it in purple. So that A, B, and C all lie on the edges of this rectangle here. There's that, there's that. I can make that one a little shorter. Let's see. Again, I want all three of the vertexes to lie nicely on the edges of this rectangle, just like that. And notice, in this picture here, we've created three right triangles that are encasing the triangle that I want to find the area of. That one right there, the one between A and C that I'm highlighting, and then this one up here. And the strategy is to find all three of those areas and subtract them away from the area of the rectangle or the area of the box. So I'm going to start by counting the lengths of all of these sides. It looks like between B and that piece right there, it's 6 units long, if you count carefully. That would be 2 units long. From A down here, there are 5 units there. 3 units right here. 3 units on the other side as well. And 7 units for that longer side. So I'm finding the area. I'm going to show my work over here just so you can see the picture. The area of that first triangle, well, remember the area formula for any right triangle, or any triangle for that case, is 1/2 base times height. The reason I can't use that for the pink triangle we grabbed in the first place is I don't know what the base and the height are because I don't know if any of my sides are perpendicular. If I drew an altitude in, I don't know if it would intersect nicely the other side. So the area of the first triangle would be 1/2 times my base of 6 times my height of 2. It doesn't matter which one's your base and your height as long as you pick the sides that are perpendicular. So 2 times 6 is 12, and half of that's just 6. For my second triangle, I can do 1/2 base times height, and those are the sides that I counted. Half of 5 is 2.5, times 3 is 7.5, or 7.5. Again, you could just do that in your calculator. And the area of the third is 1/2 base times height, or 10.5. So the area of all three of these triangles together, if I add them up, 6 plus 7.5 plus 10.5 is 24 units squared. So that's the area of the blue shaded parts I found. Now I'm going to find the area of the entire rectangle. Well, I know the entire rectangle is 7 units by 6 units, which will have 42 units squared in its area total. And to find the area of the white part in the middle, I can take the area of that rectangle, or the box, subtract away the area of the surrounding right triangles, and I get 18 units squared for the area of that white triangle in the middle that we were looking for. So the strategy is box it in, find the area of the surrounding right triangles, and subtract away. Number 4, triangle JKL is drawn inside a semicircle. Remember, that's just half a circle. JK is 16, JL is 30, and they want me to determine the area of the semicircle. Well, remember that the area formula for a regular circle is pi r squared. So if I want half of a circle, it'd be half of pi r squared. The question is, what is the radius of this circle? So it would be really helpful if we could find the diameter and just take half of it. Well, remember that a triangle inscribed in a semicircle is a right triangle, and as such I could use Pythagorean theorem to find KL. A squared plus b squared equals c squared. So 16 squared plus 30 squared is equal to whatever my hypotenuse KL squared is. So 16 squared plus 30 squared is 1,156. And if I take a square root of that on both sides, I get the square root of 1156 to be 34. So this number right here represents the diameter of the semicircle, which would mean that if I'm plugging into the formula for half of the area of the semicircle, my corresponding radius would be half of 34, or 17 in this case. Now, it doesn't specify what to round to, so if I were to leave this in terms of pi, I can do 17 squared, then divide that by 2 to find that 144.5 pi units squared would be one acceptable answer. Or if I round it, let's say to the nearest hundredth by multiplying by pi, it would be about 453.96 units squared. Now on a test I'd ask you to specify what to round to, but for now either of these are okay. For number 6, an object is made from 2 semicircles connected by the line segment shown below. Which of the following is the closest to the area of the object? Well, it looks like there's 2 semicircles here. There's this one in the middle that's taken out, and there's the full one. Let me highlight that in a different color. There's the full one altogether. So the strategy is we are going to find the area of the big semicircle, and we're going to subtract away the area of the small semicircle. So the area of the big semicircle, that would have a radius of 8 centimeters. So if pi r squared is the formula for a regular circle, I could divide it by 2 for a semicircle. So the big semicircle is going to be pi times the big radius squared divided by 2. And the small semicircle, well, it'd be helpful to know what just the distance between the center there and the edge there would be, whatever that distance is. So in order to figure that out, we've got to use this 5 centimeters right here. This distance here is going to be just 5 centimeters. That's how long it is from the edge until where the inner starts. But we also know that the radius of the large semicircle is 8 centimeters. So if I just quickly subtract them, I'll find that that little small inside radius of that white semicircle is 3 centimeters long. So if I'm subtracting away the small semicircle, I could do minus pi times my small radius squared divided by 2. Now, you could type this in as it is, or you could do a little bit of reduction first. 8 squared is 64, and 64 divided by 2 is 32. And 3 squared is 9, divided by 2 is 4.5. So if I type that into my calculator, 32 pi minus 4.5 pi, oh, not E, I want to use the pi button. I get that the area of just what's left is about 86 centimeters, or roughly 86.4 centimeters squared. So this was a shaded area problem of taking the whole semicircle and subtracting away that inner white semicircle.